Hi folks, it's Miss Gray again, and we're here for AP Chemistry. Podcast 9.3 is all about colligative properties. In other words, how do the properties of solutions change because we've dissolved things in them? So let's start off with this. Colligative properties simply refers to the properties that deal with the number of particles dissolved in a given mass of solvent. So notice it's about the number of particles. We're going to see that a lot today. Physical properties of a solution are different from the properties of the solvent. Normally, you would think water boils at 100 degrees, right? Well, not when you put stuff in it. So one thing that happens is that the vapor pressure becomes elevated. It goes up. So we call this vapor pressure elevation. And that causes the boiling point to increase as well. In addition, we will see that the freezing point goes down. That's called freezing point depression. So those are some of the physical properties that we're talking about when we talk about colligative properties. So the properties are dependent on the number of particles of the solute in the solution. This is really interesting because it's completely dependent on how many particles there are in solution. It's absolutely not dependent on the molar mass of the particle or the size of the particle or the identity of the particle. It's all about just how many of them there are. So that's what we're going to be looking at here. In this case, the one that takes into account the types of particles is molality, not molarity. So we're going to get good at calculating molality, that little m, so that we can represent the number of particles per kilogram of solvent. So we're going to look at vapor pressure lowering first of all. To lower the vapor pressure, then we have to understand where vapor pressure comes from. Essentially, it's the pressure exerted by a vapor that's in dynamic equilibrium with its liquid phase in a closed system. This is similar to the activity we did in class when you had dice and we were representing gas particles. So to evaporate, you had to have enough energy, you had to have a roll of 12 to escape the liquid phase and move into the gas phase. And then this brings us to Henry's law. Henry's law states, essentially, that the solubility of a gas is directly proportional to the pressure of the gas. So the more pressure we put it under, the more we can dissolve in there. So that's just a simple proportion that we can solve. Well, we also know that when solutes are added to a pure solvent, the vapor pressure will be decreased. And so I think it's time for us to have a picture so that we can see what's happening. You see, if we have a beaker, and in our beaker we have particles that are dissolved in there, then we've essentially reduced the number of particles of the actual solvent that are in contact with the surface. So for these to escape into the vapor phase, they have to be up on the surface, and now some of these other particles, the solute particles, are blocking them from getting out, like this one right here. That's going to prevent other particles from leaving because it's in the way. So when the less solvent molecules can escape into the liquid phase, then that would decrease the vapor pressure proportional to the number of particles that are dissolved. Remember I told you that it's going to come up a lot, the number of solute particles. So let's rank these. Out of these three, glucose, salt, and calcium chloride, which of them is going to have the greatest effect on vapor pressure? Let's evaluate this. When glucose dissolves, it dissolves as a molecule, so we get only one particle here. But when sodium chloride dissolves, it's going to break apart into a sodium particle and a chloride particle. So that's two particles in solution. Then when calcium chloride breaks apart in water, we're going to get 1 calcium ion and 2 chloride ions. So that's 3 total particles in the solution. So we could simply arrange these from those with the least impact, glucose, to those with the greatest impact, calcium chloride. So the vapor pressure will be less affected by glucose, of course, than it would be by calcium chloride. So in vapor pressure lowering, the vapor pressure decreases when vapor pressure decreases when a non-volatile solute is added to a solvent. Right? If we put something in there that volatilizes on its own, that's going to increase the vapor pressure. So we're looking at a non-volatile solute. The vapor pressure lowering is directly proportional to a solution's concentration. The more of it there is in there blocking the particles from turning into a gas, the lower the vapor pressure will be. And that brings us then to Raoult's law. In Raoult's law, we can see that your mole fraction is going to determine the actual pressure of the vapor just above the liquid. And I think I put labels on here. Let's see what we got. Oh yeah, how about there? Mole fraction of the solvent is represented by that chi, not x, but that goofy Greek letter chi, right? And then the vapor pressure of your pure solvent, before you put anything in it, is your initial P. And then the new partial pressure of the vapor is going to be discovered by applying Raoult's law. So if you're asked a question to solve for the new vapor pressure, you simply have to find the mole fraction of your solvent. We practiced finding mole fractions in the last podcast. So an increase in the mole fraction of the solute is going to reduce the vapor pressure that's over the solution. Ideal solutions, of course, are those that obey Raoult's law. Real solutions are considered to be ideal when the solution concentration is low. So just like we had ideal gases, we also have ideal solutions and real solutions. So the higher the concentration of the solute, the less ideal the solution becomes. Now let's look at what this means for boiling point, though. Vapor pressure is related to the boiling point. So I need my notes. Boiling point elevation simply refers to the fact that a solute that dissociates added to a solution is going to increase the boiling point of that solution. So boiling point refers to the temperature where the vapor pressure of the liquid is equal to atmospheric pressure. Remember, for something to boil, we have to build up enough vapor pressure so that it can actually push against the atmospheric pressure that's holding it together. And once it overcomes that balance, then we have boiling. So when a solute is added to a solvent, then the vapor pressure is decreased. And the decrease in vapor pressure means that the boiling temperature must be increased. It's going to take more energy now to overcome the atmospheric pressure that's holding it in the solution. So additional kinetic energy is required to break apart the solute and solvent interactions. And I've got an animation for us to look at so you can actually see this going on. Let's see. All right, so in the top picture, you can see basically the particles of the liquid that are simply turning into gas particles up here because they have enough kinetic energy. But just like other vapors, they go back down into the liquid once they lose that kinetic energy. So it's a dynamic equilibrium that's established. And so now let's look at what happens when we add a solute. So in this picture, this is our pure solvent. Normal boiling point for water would be 100 degrees Celsius, and so if this is water, then it would boil at 100. But then let's add salt to the mix. So if you'll notice, the little blue particles would be your sodium ions, and then the green particles would be your chloride ions. If they're dissolved in the water, then that means they're moving about in this container too, and so they're blocking some of these water particles from getting out. Then we have a lower vapor pressure, and the boiling point for a 1 molar solution of salt raises up to 101 degrees Celsius instead of the normal 100. I know it's not a great, big, huge increase, but it is significant. So it makes a difference in how we treat these. And it gives us a lot of information, too, about the solution. So that's boiling point elevation. Let's come back to our notes. So that's what boiling point elevation was all about. The temperature difference between the boiling points of the solution and the pure solvent depends entirely on the number of solute particles. Hey, look, there it is again, the number of solute particles. That's critical here. So here's the formula to calculate the temperature difference. Notice this is change in boiling point. Not what the new boiling point is, but how much it's different. So you've got to know what the boiling point is to start off with, and then add the change to it. And K stands for some constant, and M is molality. And then I is something I don't think that we've dealt with before. It's called the Vant factor. We'll get to that soon. It's our dissociation factor. Oh yeah, I already wrote all this stuff out. So the change in boiling temperature, I want to make sure we've got this change in boiling temperature, not the new boiling temperature. And then K, of course, stands for constant, because constant always starts with K, right? Right. And then M is molality, and I is the Vant factor. And again, the boiling point elevation occurs because additional solute particles will decrease the vapor pressure. So there's more pressure needed to boil than what there would normally be. Thus, more kinetic energy, and the temperature goes up. More energy is needed to break the IMFs, right? IMFs are holding this liquid together. So if we have to overcome stronger IMFs, we're going to need more kinetic energy. Let's look at that Vant factor. Little I is not for the square root of -1, not in chemistry class anyway. It's the number of particles into which the added solution or the added solute dissociates when it's in solution. So this entirely depends on the solubility. For all molecular compounds, the Vant factor is equal to 1. So for glucose, remember I said that's going to have only one particle in solution because it's a molecular compound. That's what molecular compounds do. But for ionic compounds, those that are strong ions, the Vant factor is dependent on the number of particles it dissociates into. So by strong, we mean it's soluble, right? Or considered to be aqueous in solution. So you've got to know your solubility rules, or this is going to be really hard for you. Let's do a couple quick examples though. Sodium chloride, we talked about, breaks into sodium ions and chloride ions. And so the Vant factor for sodium chloride is 2 because I have one of these plus one of these for a total of 2 particles in my solution. Now, Pay attention. If I have a 0.1 molar sodium chloride solution, that means, we've done this before, that means I have 0.1 molar sodium ions and 0.1 molar chloride ions in my solution for a total of 0.2 molar, right, ions in my solution because my Vant to Hoff factor was 2. Now sodium phosphate is going to break apart into 3 sodium ions and only 1 phosphate ion. That's the mole to mole ratio in this molecular formula. So the Vant to Hoff factor here is 3 of these plus 1 of those for a total of 4. Vant to Hoff factor is 4 for sodium phosphate. So the freezing point depression is also going to depend on the number of particles. The solutes disrupt the normal geometric pattern for that lattice, the crystal lattice, to form. Since there's solute particles getting in the way of the crystalline lattice, then your pure frozen solvent is going to stay in solution rather than actually connecting and crystallizing. So additional kinetic energy must be lost in order for the solidification of that solvent to occur. Here's our equation. It looks a lot like the boiling point elevation. See, again, we have the change in temperature, not the new temperature. We have some constant, K, molality, and the Vant to Hoff factor. So T sub F, again, is the change in the freezing point temperature. And then K is for constant, because constant starts with K, right? At least it does in German. And then the freezing point temperature or the boiling point temperature can be used to find the molar mass of a substance. That's really handy for scientists to have lots of different ways to find molar mass because that can tell us so much about the substance we're working with. So you've got this table. We're going to be using it now in our examples. So make sure that you have this one handy. I'm going to be referring back to it. In example 1, we're given this information. A solution is prepared by dissolving 4.9 grams of sucrose in 175 grams of water. We're asked to calculate the boiling point of this solution, knowing that sucrose is a non-electrolyte. Non-electrolytes, remember, don't break apart into ions. So our Vant to Hoff factor here is 1. So here's the equation for boiling point. And what I need to know is what's the boiling point constant for water. Water's our solvent here. So let's come back to this slide before and find the boiling point constant Kb for water is 0.51, and here's our units, degrees Celsius times kilograms divided by moles. All right, you ready to solve this problem? Let's take care of this. So first of all, I think I better find the molar mass of sucrose. Molar mass is going to be 12 carbons, 22 hydrogens, and 11 oxygens. That's a lot of stuff. I expect a pretty high molar mass here. And indeed, I do have 342.34 grams per mole for sucrose. All right, and now I have grams of sucrose and grams of water. Guess what we're going to do? We're going to go to moles. You betcha. So let's find 4.9 grams. And for every 1 mole, I have 342.34 grams. That gives me 0.082. No, that's my molality. Nowhere did I find this. I'm just skipping right ahead. Time for a calculator. Hang on, folks. Sorry about that. I was looking at the wrong number. So for the number of moles, I get 0.01431 moles of sucrose. And now I want to find the molality, because I can't solve for boiling point without knowing the molality. So that means moles of solute, 0.01431 moles of sucrose divided by kilograms of solvent. So my solvent is water, and I have grams. Let's move the decimal 3 times over. So that's 0.175 kilograms of solvent. That will give me my molality, so let's take moles and divide by 0.175 kilograms, and that's where that number is, 0.082 molal. Now that I have the molality, I can go ahead and find the change in the boiling point temperature. So delta T sub B is going to be equal to my Vant to Hoff factor of 1 times Kb, 0.51 degrees Celsius times kilograms over moles, and then multiply that by molality, which was 0.082 moles per kilogram. So what do we got? A change in the temperature of 0.0417 degrees Celsius. So, did I answer the question? It asks us to calculate the boiling point of this solution. I have not yet answered the question. My new boiling point is going to be the regular boiling point of water plus my elevated temperature. The new change here is 0.0417. So we add those together for a new boiling point of 100.0417 degrees Celsius. Now I have answered the question they asked. So put a box around your answer, because you know that's the way I like it. Okay, we're going to do another one, only this time we're going to work with the freezing point for water. Freezing point for water is normally 0, right? But now we're going to stir 320 grams of solid calcium nitrate into 2,500 milliliters of water. So use the density of water. We're going to change milliliters to kilograms. You ready? That's 2,500 grams. Move your decimal 3 times. So that gives us 2.5 kilograms of water, 2.5 kilograms of solvent. How about solid calcium nitrate? We better know how to write this chemical formula, calcium nitrate, and that will allow us to get the molar mass. We need to know how many moles of calcium nitrate are in 320 grams. So let's see, this molar mass, what do we have? 1 calcium, 2 nitrates, and 6 oxygens adds up to 164.1 grams per mole. So let's find molality. No, I'm not ready for molality. I need just number of moles of calcium nitrate first, right? So we'll start with 320 grams, and then for every 1 mole I have 164.1 grams. So I have 4 moles, 1.95 moles of calcium nitrate. Now I can go to molality. So 1.95 moles of my solute divided by the kilograms of solvent, 2.5 kilograms of solvent. That leaves me with a molality of 0.780 molal. And now I'm ready to calculate the freezing point depression. So what's my change in the freezing point of water? How many particles does calcium nitrate break apart into? Let's see, I have calcium, which is a +2 ion, and there's just one of those. And then nitrate is a -1, and this formula tells me I've got 2 of those when this breaks apart. So my Vant to Hoff factor is 3. My Kf for water, let's come back to our table and find it. Wow, I filled up all of this with my writing. It's 1.86. Did you find that one? You have your own table. Look at your own table. 1.86 it is. 1.86 degrees Celsius times kilograms per mole. And what else do I need? I, K, and M molality, 0.780. That is moles per kilogram. I want to make sure that everything's canceling correctly. Look, I end up with degrees Celsius, and since I'm trying to find temperature, I'm happy with units of degrees Celsius. So my change in freezing point was 4.35 degrees Celsius. That was a lot more than the last change, right? So what's my new freezing point? Because it asks us to calculate the freezing point, not the change in the freezing point. So I take my 0 degrees Celsius that water normally freezes at and subtract from there this change of 4.35 degrees Celsius. And of course I get negative 4.35 is my new freezing point for water when I add calcium chloride. This is why, calcium nitrate. This is why calcium salts are often used for de-icers, because they have a higher Van 't Hoff factor than sodium. Is that how you spell de-icer? Oh well. Let's see, do we need to do another example? Let's save this one for in class. We'll save the next two for in class, for that matter. No, actually, example 3 we'll do for a warm-up, but example 4, I really want you to be able to see this and come back to it, because this is critical that you would be able to calculate the molecular mass of some solute based on its freezing point depression. So let's say we have a solution that has 4.5 grams of some non-electrolyte, so our Van 't Hoff factor I is equal to 1. And it's dissolved in 125 grams of water, and it freezes, the water now freezes at negative 0.372 degrees Celsius. So how will we get to the molecular weight of the solute? Here's what we got to know. Molecular weight is grams per mole. I have my grams here, so what I've got to find out is moles. As usual, to start a problem, we got to find a way to get to the number of moles. No big shock there, is it? That's what we're always doing, trying to figure out moles. So here we go. I'm going to use my freezing point change to get to moles, because I know it's the constant times the molality times the Van 't Hoff factor. And I know all of these except for molality. So let's solve for molality. That's going to be my freezing point, my change in freezing point, I should say, divided by the freezing point constant times my Van 't Hoff factor, which is just 1. So this is going to be really easy. So I take my negative 0.372 degrees Celsius and then divide by my K sub F, which for water is 1.86 degrees Celsius times kilograms over moles. And then I multiply that by my Van 't Hoff factor, which for non-electrolyte means just 1. Does not break into ions. So what's my molality in this solution? Again, 0.2 moles per kilogram of solvent. So now here comes the critical step. If I have 0.2 moles for every 1 kilogram, then how many moles will I have when I have 125 grams? So that's 0.125 kilograms. So use a simple proportion to solve for x. That means in this particular solution, I have only 0.025 moles, not 0.2 moles, because I don't have a whole kilogram, I only have 125 grams. So now is the time when we can find our molar mass. Molar mass is grams per mole. So I take my number of grams, 4.5, and I divide by my number of moles, 0.025 moles. So my molar mass here is 180 grams per mole. That's how we use freezing point depression, or you could use boiling point elevation to first get to molality, step 1, then change molality to moles in step 2, and then take the number of grams divided by the number of moles in step 3 so you can obtain your molar mass. That's all there is to it. So rewind this, use it again when you're doing your homework, when you're trying to solve your book problems involving freezing point depression and molar mass calculations, because you'll probably need to see this again. So I hope you followed along with your calculators, because you should always check my work. I make mistakes every now and then. Great, we'll practice more of this in class, and I'll see you guys soon.